Hello. When we're tracking objects, occasionally this tracking gives us a little bit of a problem. Maybe objects pass behind obstacles, or maybe if you have a couple of moving objects that you're tracking, that they may pass in front of each other or behind each other. Therefore, there may be some question about the identity of the two objects. So if you see two people walking together and then they separate like this, well, did they sort of meet and then talk and then separate this way, or did they just pass in front of each other and carry on? So that's kind of the essence of the problem. And what we're going to look at now is not really you might say, the best or only way to solve this problem, but is one of the interesting ways to solve this problem. And we're going to have a look at this. We're going to do this in a probabilistic kind of way that keeps accumulating more and more evidence and tries to sort out what the best assignment of identities to the detected targets are. And one of the nice ideas about this is that we don't have to make that we don't have to make that assignment, we don't have to make that decision when we first collect the data, when we first observe a particular person or a particular target. Here we're going to set it up as a kind of probabilistic network so that we can propagate the evidence that we observe from frame to frame and ultimately make a decision when the probability gets to be high enough. So here's kind of the case of normal target tracking. So we've got two targets in this image in one frame, and then we kind of go to the next frame, and we've got a couple of targets, and then the question, and this sort of carries on for a while, and the question is, well, which way should we pair these two targets together, this way or in this way, or this way and this way? And in general, if you've got R targets in the first frame and L targets in the second frame, this is a kind of huge combinatorial type problem to be able to pair these together. That one is there is because maybe we don't even maybe we haven't even necessarily observed the target in the next frame. Maybe we need to match it with something else, like maybe the target has disappeared behind an obstacle or something like that. Now, in many cases, we don't have a very tough problem, because if the video is running fast enough, then targets hardly move from one frame to the other, and except in the cases where they overlap with each other, sort of pass in front and behind, generally we don't have any real trouble with identifying which target in the first frame is the one that we can match with in the subsequent frame. And as we've seen also, the Kalman filter is quite good at making these predictions. So we can use those predictions as well to sort of match up with the observations. But here's a case, a more realistic case, where we might have particular problems. So we've got sort of frames 1, 2, 3, and 4 right here. And if you'll notice, there is a car here, car number 1, car number 2. And in the next frame, they're a bit closer together. And in the third frame, they overlap. And in the fourth frame, they've separated. And meanwhile, a couple of other targets have sort of moved into the scene. So we've gone sort of from 2 targets down to 4 targets. And somehow we have to identify which of these targets from here are to be matched with the ones that we've got down here. In the case of the people, it's not so difficult. They have not really moved very far, but as you can see, the cars can move, because they move faster, can move a more considerable distance between frames. So generally, tracking kind of breaks down when objects get very close together or they occlude. They don't need to actually literally pass in front of each other. It's just usually when they're even standing very close to each other, the target detection algorithms often group them together into a single target. So what goes from originally 2 independently moving objects can now be treated as just a single moving object. And this little diagram here sort of sums it all up. We initially have kind of 2 moving targets moving along. They get close to each other, and there's a bit of a mess where we don't know exactly quite what's going on. And then people sort of separate out again, and the targets move out again. And then, well, we have the question of, well, is this one, sort of person A or person B? Or indeed, it could even be a person C, because it might be that these were, B was originally, say, 2 people moving arm in arm, and then out comes, something new, or whatever, one of the 2 people, whereas the other person sort of paired up with originally with A and then moves off in the other direction. So there's a variety of different hypotheses that could come out of this. And if you look at the references for the lecture, we have a nice paper for this. It gives an outline of the method that we've got right here. It sort of lays out the basic principles of how we can keep track of the individuals and make also hypotheses about who might be the targets, or what might be the targets, and how we might match them up. Okay, so we're going to take the target detection and tracking work that we've looked at previously, and we're now going to extend it a little bit. We're going to need some sort of a process that identifies when trajectories get together and merge, okay, because of some kind of occlusion. We're not going to go through the algorithm exactly how that happens. We're going to assume some sort of process, computer program can do that already. What we're going to do is what comes afterwards to help try and identify which person is which, or which target is which. Okay, and for each of those little bits of trajectory that we've broken at the occlusions, we're going to have that sort of track I. We're going to have create a Bayesian network, a probabilistic reasoning type network, where there's going to be a node X for each of those different tracks. Okay, and it's going to inherit, as we'll see in just a second. So here's a kind of model of what's happening. So here's our image plane, sort of indexed by row and column, or X and Y. And here's a third axis of time. So we're going to look at how that trajectory evolves over time. And at each of those times, we're going to detect a person, detect a target, moving target, something like that. And here is one of those detected targets. So this is number 2. And you can see as we move our image plane through time, you can see that that target moves a little bit along here. Similarly, here's another target number 1. And at some point, they get so close together that you can't tell which one is which. So we just think that's just a single target that's going to be moving. We've detected that that's different than the background, so we keep track of that for a few more frames. And then maybe something happens. Maybe we lose it because they move into shadows, or they move behind a tree or something like that. And then it reappears. There's a group here, and we just have a single target, so we call that S4. And then maybe later at some time, this group here breaks up and goes off in 2 different directions. So that's going to be trajectory 5 and trajectory 6. So with that sort of description of what's happening sort of in the scene and the image, we can now build up the start to a probabilistic model, or a little bit of Bayesian network. And so our Bayesian network is going to be indexed. So these are nodes x1, 2, 3, 4, 5, and 6. And they're really about target trajectory S1, S2, 3, 4, 5, and 6. And associated with each of those nodes, we have a set of hypothesized persons or targets. Okay, and well, initially they start with just a single target when the trajectory first forms. And then when they merge, okay, then we've got 2 possible hypotheses, P1 and P2, that we've inherited. And we also create a new one, P3, because maybe, I don't know, maybe it's the front and the back half of a lorry, and they're sort of connecting together to make a new object, a new complete lorry or something like that. And anyway, then there's a bit of a break here, and we don't really know what's happened in that break. Maybe they moved behind an obstacle. It could be that they moved behind an obstacle and another person appeared, sort of like, a bit like in a magic trick or something like that. So again, we add a new identity in at this level. And then when the 2 trajectories break, okay, then we get some additional identities. So you can kind of see how we're sort of gradually building up more and more of a description, and we're also accumulating more and more different hypotheses about what and who we might be tracking. So we're going to need a way to estimate the probability that each of these different hypotheses is the correct hypothesis to explain that trajectory. And that's what the Bayesian network is all about, is estimating those probabilities, and also propagating the probabilities back and forth, because you may have good evidence at this level, but maybe not at that level, and we can use that evidence to propagate backward as well as forwards. Well, the core to doing all of this evidence matching is the evidence itself. And in this case, It's the color of the target that we're going to use as the, say, the raw image evidence. So we assume that we've got some sort of a binary mask of the target. We've seen that already a lot with the target detection, where we thresholded the probability, and then the pixels in white are where we think the target is going to be. And we can use that mask then to go back and look at the original image and extract all the colored pixels from that. So that gives a set of pixels with their associated red, green, and blue value. With all those pixels, we can then compute what's called a red, green, blue histogram over all those pixels from that target. Now this is a big, can be a big histogram. It's got three axes. It's got a red axis and a green axis and then a blue axis. And it's a three-dimensional histogram. And every time we see one of the target pixels, we can increment the value in that histogram. So we'll call it histogram 1 for target 1. And this gives us sort of an accumulation of all of the colored pixels. It gives us a kind of descriptor of the object. So if a person is wearing let's say a blue shirt and a black pair of trousers, you would expect to find a big cluster of pixels around the bluish area of the histogram, and also a big cluster of pixels around the blackish area of the histogram. And that would be a kind of descriptor, and maybe also a bit for, sort of skin color or something like that. That would be a descriptor of that person. It's a little bit unique. And we do this not just for the frame that we've detected, but actually we do it over all the frames that we've detected in this trajectory. So because we're assuming that we're looking at the same person or group of people over the entire trajectory. So we accumulate all the evidence from all of those frames. Okay, so that might give us, up to sort of 20,000 pixels if you're looking at sort of 30 or 40 frames times a few hundred pixels or something like that in each of the segments. And so it can build us quite a reasonable descriptor. Well, okay, so we have a descriptor now, H1 for target number 1, and a descriptor for, this target number 5 or whatever. We want to know, well, how well does this descriptor match that descriptor down there? Okay, so now, that means we now need a way of matching colors, or color histograms. And so we're going to use something called the Bhattacharya distance in order to do that. So the first thing we have to do in order to do that is we have to normalize our histogram. So originally we had all the individual counts, but we want to normalize it so that all of the counts are, rather than individual counts, they're sort of floating point numbers, and all of the numbers in the array, this three-dimensional array, will add up to be equaling 1. So we just take the original array and divide by the sum of all those numbers. Okay, so that's for the first matrix, and we do that for all of our matrices. That gives us our sort of normalized descriptor of the matrix. And then we can use the Bhattacharya distance, and that's defined by this formula right here. So if two matrices are equal, then that means for each red, green, and blue cell in that matrix, they're going to have exactly the same values, and we can sort of multiply them together. If we multiply them together and they're equal, then they're going to be, the square of the thing. We take the square root, and we've added it all up. Okay, that again is going to equal to 1, because that's what we've done for the normalization. And that will give us a distance of 0. So that's good. If the two matrices are identical, the two descriptions are identical, we get a Bhattacharya distance of 0. And similarly, if the matrices are very unlike each other, we might, at the worst case, we might get a distance of 1. So the bigger the distance, the less similar those two matrices are. We're going to make the assumption that there's a little bit of noise, and so therefore, if this distance is small, it's still likely to be the same target. Now we have a little practical consideration to deal with here, and that is usually our colors are quantized to 256 different values. So we have 256 red, 256 green, and 256 blue, which can make a very large sort of matrix that we have to deal with. And that's too big of a matrix, and it also means our values are too spread out. We don't have enough actual values to make a good sort of filling out of the values in that matrix. And so what people traditionally do is that they group the pixel values together into blocks of pixels, and therefore for each of the colors, maybe instead of having 256 values, you only have 8 different values. So that means our matrix is now 8 by 8 by 8, or 512 values. And then, therefore, the 20,000 observations that we made, the pixel values, sort of fit into that and give a more reasonable sort of distribution. But that's just a kind of practical consideration that you have to think about according to how many pixels you have. Right, so let's go back to our network. So we have our label nodes for each of the segments, and we're going to extend that with two other kinds of nodes. So the first one is a data matching node. That's called the Y node, and that's where we do our histograms matching. We want to estimate the probability that the currently observed histogram for a new segment matches one of the histograms from one of the previous segments. Okay, one of the different identities. And we also have a kind of restriction node that enforces a kind of mutual exclusion between sibling nodes. And the reason for that is that if a person has gone off along one of the trajectories, they can't go off on the other trajectory as well. So this is a good way of kind of forcing the network to decide which way did the person go. So here is a little bit of an extension. This is our network before with all those X nodes that we had, and now we've extended it with our data nodes here. So we've got the Y nodes right here added, and then there's also a restriction node here, because it says that any person which was observed in this trajectory couldn't be observed in that trajectory at the same time. Well, how are we going to actually come to some conclusion in this network? So this is a kind of a Bayesian network, and what we're going to want to do is we're going to want to find the labels, okay, which are our identities of who's in which trajectory. It maximizes a kind of probability of given both the observed data and also the kind of restrictions that we want here. Okay, and that will give us the probability that each individual person is observed in a given track. And we're going to do this using a standard Bayesian network propagation type algorithm, and we're not going to go into the details of how we do that here. Now, let me just jump ahead to slides that have a picture. So as you can imagine, we're tracking this person over time, or these people over time, and while we're not working at the level of individual frames, we are working at the level of individual tracked segments where people cross in front of each other or maybe tracks get broken because of either algorithm failures or occlusions or things like that. So you can imagine that over time, the network keeps getting bigger and bigger. So here's an example of a network that's getting bigger, okay? And it's this is the initial time, and as time goes on, it keeps adding more and more nodes and more nodes. And if we're going to have an algorithm using a Bayesian network type algorithm, okay, the probability for the full evaluation of the network, the probability has to flow backwards and forwards through this network until the network converges. And as you can imagine, as the network keeps getting bigger and bigger, this becomes more and more of a computational burden. So the developers of this work really made two sort of simplifying assumptions that help make the evaluation of this network much more efficient and allow something closer to real time. Okay, and the first is doing a little bit of an incremental evaluation. Effectively, you want to know, what are the identities given all of the image evidence from 0 to time t and all of the restrictions from 0 to time t. And they showed that, well, this full evaluation of this probability here is proportional, okay, that's the proportionality constant, to some recent evidence plus a block set of evidence that was done in the past. And so what that allows them to do saying is, if you can sort of freeze this evidence, you don't need to keep reevaluating, you just need to reevaluate the new bit right here from a kind of fixed time up to the current time. And so they did that in sort of blocks of t frames. And the second thing that they did was that they did a kind of freezing of that. So although in theory all of the data can propagate backwards and forwards all the way, and new evidence might be the kind of evidence that you finally need to evaluate and resolve some sort of ambiguity you had previously, they say, well, we don't need to go back too far, we'll just assume that we made certain decisions. Okay, so we've So the way that they propose to solve this problem is that they after a certain point, they just freeze all but the n most recent nodes. So they make some assumption that previous nodes are always fixed. Maybe there was a mistake, maybe not, but we're just going to assume they're fixed. And then we're going to freeze those, and then we're just going to be doing our probability propagation just on the more recent nodes for that. Okay, and again, there we might get some future evidence that might correct some of those nodes, but the ones that we've frozen, those are sort of permanently done. Okay, so here's an example of that, and here's a bit of a network at a given time, and the dark shaded nodes are the nodes which have been frozen. Okay, and that's a case of saying, well, this is definitely a particular identity. Unlike previously, when we're dealing here, we have, for example, all 5 possible identities are in play. When you freeze a node there, you basically say, well, okay, so P3 is the most probable of those identities, and therefore we'll say, well, this node is fixed to P3. And because of the restriction, that also removes P3 from that node right there. Right. Okay, so here's at a given time, and this node is frozen, and then now the network grows a little bit more, and here you can see that network has grown a little bit more from sort of here downwards, and at a certain point, the analysts say, okay, well, let's freeze this bit of the network right here. We'll just assume that we know all the identities there, and then that sort of propagates in here, so that stuff can propagate back and forth and converge, but we're going to fix that. And then here's another later time where the network has gotten even a bit further. It's sort of, before we were down to sort of here, and now they added a bit more, and we maybe assume that this is enough data right here, or maybe some objects have left the scene. We can't make any more decisions about them, so we'll just freeze all of that network, and we still have the live bit of the network where we can still be adding new data and new evaluations. Anyway, so it's a kind of computational technique that allows us to work over the whole network in a practical kind of way without having to do all the computation back and forwards all of the time. So really this is a technique that we can use for dealing with occlusions. When objects cross in front of each other or behind obstacles, we kind of lose track of, who's who, okay, which object has the identity. Fortunately, we've got our color, a little bit of color that gives us some clue as to which obstacles, which targets may be which when they reappear from behind either each other or the obstacles. And so we put all these pieces together as a kind of probabilistic model through a Bayesian network, and we can propagate the probability of each of the different identities through that network. And that's sort of like the full general solution to the problem that they adopted, but they recognized that they needed to kind of freeze the network occasionally to make the evaluation computationally tractable. Right, so we're going to look next at some examples of how this was used for some of using this network probability for a tracking example. Thank you.